Awesome. Yeah, let's go. All right. I know, I'm sorry. That was a really fun discussion. We'll have to continue it, but thanks for the insights, Professor Wagner. Elections are very interesting data science problem. All right. So today we're talking about models. Um, a lot of models are used to predict outcomes of elections, so very relevant. And just kind of going over what we went over this week so far, how that all fits in. So on Monday, we talked about simulation. So how can we actually simulate values from a random quantity? So we saw an example of this where we wanted to simulate our happiness score for each day of the week based on whether we sleep in or wake up. Then we talked about some of the kind of fundamental rules around probability. How do you actually calculate probabilities? Went over 4 different ways to do that. Saw some examples of different problems where we can use those ways to calculate probabilities. And then on Wednesday, we started going into how do we actually sample data? What are properties of a random sample versus deterministic or sample of convenience? And towards the end, we started talking about how distributions of large random samples are a good way to understand the distribution of the population probability distribution that we're trying to, infer something about. And so the example we saw that was a die. And so, we know that the theoretical probability of each of the individual values in a die coming up is 1/6. But if you try to simulate, and you can simulate maybe 10 rolls of a die, 100 rolls of a die, as you do in more and more rolls, the number of times that you see each of those numbers come up gets closer and closer to 1/6. So you saw an example of that where we did 10 rolls of the die and we never even rolled a 2, we never even rolled a 5 in those 10 rolls. And so the empirical distribution of numbers looked very different from what it should. But then we saw that as we increased to like 1,000,000 rolls of the die, then pretty much each of the numbers came up 1/6 at a time. So we saw how that empirical distribution got closer and closer to the actual probability distribution. So today we'll just review that a little bit quickly in another example, and then actually start talking about models, and specifically statistical models that involve chance. And then finally, we'll conclude with talking about how do we actually assess these models. So a few announcements. We have vitamin 16, per usual, so please complete that before Monday's lecture. Homework 5 has now been extended by a couple days, so it's due tomorrow. And project 1 has also been extended by a couple days, so it's due on Sunday now. And homework 6 is out today, so that's due next Thursday. We've also put up some guides for you. So there's this really great guide on just understanding code. So please check this out. It's super helpful. And if you've been having blank submission issues on OKPy, please check out this link in the slides. So that will help you resolve that. And lastly, as you mentioned last time, we'll be accepting confessions for any violations of academic integrity until Saturday. So please fill out the form. Cool. So those are announcements. So if you guys have the slides open, you should be able to check the links. The links are also there at the top of the Data 8 website. All right. So quick review of distributions. So we talked about, we've seen so many distributions in this class, right? We've seen categorical distributions, which is basically, if you have a categorical variable that can have different categories, it's essentially all the unique values, and then, how often each one comes up. And then we talked about numerical distributions, where you have some variable that takes on kind of infinitely many values. Basically, it can just be any number. And we talked about how for those type of distributions, if you want to actually see them, typically you have to bin them first, because you have so many different types of values that you can have. It's not just 5 or 6 different categories. So in that case, if you want to actually get a sense of distribution, you typically have to bin them into kind of bins of different sizes, or maybe the same size, and then just count up how many times the value comes up in each of those bins. And so that's how we can create a distribution for numerical values. And so both numerical and categorical, those are just kind of 2 types of variables that we'll be talking about in this class. And so both of those variables have probability distributions. And the probability distribution is kind of the theoretical true probability of any of those values coming up. And so we actually just define this. It's basically all the possible values that your variable can take, and the probability that it's going to take that value. So this is the kind of how often those values should come up if you simulated values from this variable many, many times. And then if you actually observe like a sample or you actually simulate some instances of this variable, then what you see is an empirical distribution. So this is kind of what you actually observe. So this is kind of like what you actually see in real life. And so in this case, it's going to be all the observed values that the variable took, and then the proportion of times that each of those observed values came up. So quite similar, but the main difference is just kind of what's the probability of value should come up versus how often did it actually come up. That's the main difference here. And then we talked about the law of large numbers, which basically said that if you have a really large sample size and you take a lot of independent draws or observations of this quantity that you're interested in, you should see that the empirical distribution, which is how often each value actually comes up, gets closer and closer to how often each value actually should come up. So the probability distribution. So I saw an example of that. And so let's go through one more example of this. So we were looking at this flight of, this data set of United flights from the summer of 2015. And so we had this, let's actually just read it in again and take a look at what it contains. So it contains, the flight numbers, destination, like what was the delay in minutes. And so one thing you might want to do is take a look at all the delays of the flights from that summer and just get a sense of what does the distribution look like? Like how often do you get a delay that's just like, within 5 minutes versus a delay that's over like 30 minutes? So we could actually take a look at that by visualizing distribution. And so, of course, the first thing we need to do, because this is a numerical variable, delays in minutes, so you could have basically any possible value for that, we need to make some bins first. So let's actually do this, and we can actually visualize it as well. So let's do United bins equals np.arange. So we're gonna do bins from -20 to 201 in increments of 5. And we will then do united.hist, and then we specify which column you want to draw the histogram of. In this case, it's delay. And then we just specify which bins we want. And so I made these bins kind of beforehand. It's a little bit arbitrary, but you can make them whatever you want, essentially. And so if you make the bins, this is kind of what we get a sense of what it looks like. So most of the delays are actually kind of near 0. But then you do have some delays that go out. So you do have like some flights that are as delayed as like 100 minutes, which is pretty bad. And then even like 50 minutes. So you can kind of see what the shape of this looks like. So that's how you can kind of interpret this. And so again, remember with a histogram like this, area is kind of proportional to how much stuff there is in that bin. And so most of the stuff is near 0. That's essentially the main takeaway here. So most delays are kind of near 0. But you do have a lot of delays that are kind of well beyond 0. And then you do have some delays that are actually negative. So you have quite a few that are, the flight actually leaves a little bit early. Never happened to me, but the data doesn't lie, so I guess I can't argue with it. And so this is the population distribution. So this is the actual delays of all of the flights in December 2015. So that's the population that we're trying to study. So this is the kind of the true theoretical distribution of everybody, of all the flights that actually happened that summer. And so one thing we could do is imagine that maybe we didn't have a way to collect all of this data. And maybe it's really expensive to like search through all the flight logs. So maybe what we did instead is we just maybe took a random sample. Maybe we like called up people who are like United customers, or maybe called up pilots and just asked them, hey, like what was the delay of your flight today or something like that. So there's some proper way that we did this where we actually understood beforehand what was the probability of selecting each person and all of that. So we like satisfied all the conditions of a random sample. And we looked at the delays of just that sample. So maybe it's like a much smaller sample than all of these 14,000 flights. So we could actually simulate that right now. So we have this table, and what we could do is we could say united.sample10, and this is going to basically simulate getting 10 random flights from that summer. And then we could plot the histogram of those flights. So then we could do .hist delay. Let's use the same bins. And so now we get a distribution like this. And so what we're seeing here, this is an empirical distribution. And so this is the empirical distribution of one particular sample that we got of size 10. And so you can see that there's some things about this that look similar to the probability distribution in the sense that you have a lot of delays near 0. So that's kind of pretty similar. And then you do have some delays out here. But what's interesting is the heights of these bins are slightly different, right? So if you look out here, you had these ones around 0, and you had a height of like almost 2 here. And then the one, once you got to 50, everything was like pretty low. All the bins weren't that tall. Whereas here, we happen to get actually like, just by chance, we happen to sample like a lot more flights that were delayed by 50 minutes. So there's some differences there. And then every time that we run this code, it's also going to give us a slightly different distribution. So we can take another sample of 10 flights and see what that looks like. So if we run this again, now we get something quite different. So now we got some flights near 0, but then we also got some delays that are like really, really out here, like almost 3 hours delayed, 180 minutes. So you can just see how kind of it jumps around a little bit. So basically what we're seeing down here, this is empirical. And what we're seeing up here, we're going to actually consider this the probability distribution, because the probability distribution is with respect to a population that you're trying to study. And so in our case, the population that we care about is all flights in the summer 2015. And because we have all of those flights, that just is the population. It isn't actually a sample. This is just all the flights. So that's why this is a probability distribution. So this is an example of an empirical distribution. We kind of randomly sampled from that. And then again, we want to show this law of large numbers so we can see what happens when we increase the sample size. So instead of 100 flights, let's actually sample 1,000 flights. And so now we see something that looks a lot more like the probability distribution. And so again, this is just kind of law of large numbers in action once again. So, if you take a lot of samples of this quantity, the empirical distribution that you observe in your sample is going to look more and more like the probability distribution of kind of the entire population. And so that's what we're seeing here. All right, so that's kind of law of large numbers again. Any questions about this before we continue? Let's go back to the slides. Oh, sorry, you're asking to go back up to the probability distribution right here. Yeah, so again, the distinction here is if there's some population that you're trying to understand something about, if you have all the values in that population, that is the probability distribution. So I made this analogy the other day when we were talking about, let's see, one of the party affiliation, political party affiliation of all of Berkeley students. If you had access to all of Berkeley students, you have the population. That is a probability distribution. It's not empirical. It's a theoretical distribution because you have all the students. But typically, that's hard to do in practice. Typically, it's going to be hard to actually get the entire population. And so that's why you typically have to do things like sampling. And when you're sampling from the population that you're trying to understand, you're typically going to have like a smaller set of people, smaller set of individuals. And so that's where it's actually an empirical distribution. So that distinction is really clear. It needs to be really important there. And so, yeah, someone asked, is the population larger than 1,000? Yes. So the population is actually about 14,000. So you can see here, when we looked at this entire table, there's like 13,815 rows emitted. So it's roughly 14,000 flights in this actual population. And then we sampled 1,000 from them. So the 1,000 is still going to be quite a bit smaller than the entire population. Cool. All right, so that's distributions. And the reason large numbers is important, why it's actually useful, is now getting to inference. And this is kind of really core chunk of like why data science exists, why it's powerful, why it's useful. And so when we talk about inference, and specifically statistical inference, we're using in the context of making conclusions based on data in random samples. That's really kind of the goal of statistical inference. And so the idea is, in an ideal scenario, you would love to be able to get all the data in the population. You'd love to be able to get all of the information about, this particular quantity that you're trying to understand. But typically, it's just not a feasible thing to do, mainly because of time and money. And so you're typically going to have to do some sampling of your data. And so the idea is you want to make conclusions about the population using this smaller sample that you have. That's statistical inference. And typically, it's going to be in the context of like guessing the value of some unknown number. And so we'll go through like some examples of what that means. But typically there's like some number that you're interested in knowing about the population. So for example, I want to know what percent of the UC Berkeley students are independent. That's a number. I want to know what's the median flight delay of all of the flights in the summer of 2015 operated by United. So that median flight delay, that's a number. So typically there's like some number that you're trying to understand about the population. And again, the best way to calculate it would be to just get all the data from the population and then calculate the number and you're done. But it's really hard to do. So we're gonna have to sample some data and then try to use the data that we've sampled to get a guess at what that number actually is in the population. And so that guess that we are going to create from our sample, that's called an estimate. And so it's an estimate because it's not going to be perfect. It's probably not going to be the exact number, but the idea is you want to try to get that number to be as close as possible so that you can actually trust the number that you got out of your sample. And there's two kind of key things here to keep in mind. So this unknown number that you're trying to understand, that's a fixed number. There's like some true value there. But the estimate that you're going to get actually depends on your random sample. And we just saw that. So, when we sampled those 10 flights from United, we had a bunch of flights near 0. And then initially we had a bunch of flights kind of around 50 as well. But then we did another sample of 10 and there were a bunch of flights near 0, but then a bunch near 180. And so, the flights changed quite a bit in that sample. And so if you were to do something like calculate the average delay of each of those samples, they would be quite different actually because the values you got were so different. And so the idea is your estimate actually depends on your random sample, depends on the values that you happen to get. And so that's also very important when you're trying to create an estimate, to keep in mind that, oh, actually there's some variability in the data that I'm getting here, and you just have to kind of keep that in mind. And so we'll go through like how we actually do that. And so in this entire kind of framework of there's some number that we want to know and we want to try to estimate it, there's some terminology we're going to use here just to make it a little bit more formal. So we're going to call that number that you're trying to understand in the population, we're going to call that the parameter. So that's a parameter of the population. So average flight delay is a parameter of the flights that United operated in 2015. The percent of people that are independent, that are voting independent or politically affiliated with independent, that's a number associated with the population of UC Berkeley students. And then the guess, the estimate of that is a statistic. So this is a number that's calculated from the sample. And so any number really that you calculate from a sample is a statistic, and typically statistics will be used to try to guess at a parameter of the population. So that's the main distinction there. And so just kind of repeating that again here. And so let's see some examples of this in the context of our United flights once again. So I was talking about maybe like average flight delay. And so one thing we could say is, let's say we're interested in the median flight delay of all the flights that happened that summer. So we could actually find the population parameter. This is like the true value of the population. So the true median of all of United's flights in December 2015, we can just find that because we have all the flights with us. So how we do this, we do np.median united.column delay. So if we run this, we get 2.0. So it looks like the median flight delay is 2 minutes. All right. And so that's the actual kind of true value in the population. This is the parameter we're interested in. And then if we wanted to try to estimate, so again, let's imagine that we didn't have this entire United table and we could only see like some of the flights. We had to sample them. And we wanted to guess at what the median is. How do we do that? So it'd be quite similar, except we would do np.median on a sample from this table. So we could do np.median united.sample. Let's start with 10 maybe. So we'll do a sample of 10 flights and then column delay. And so now our particular sample that we happened to get this time, we did united.sample 10. We took 10 random flights, took the delay column, calculated the median of that, happened to get -1 here. And I could run this again to see what we get. All right, so now we got a median delay of 13.5. Run it again, now we got -2. So you can see that it jumps around quite a bit, what median we're gonna get. And why is that? Because we saw how with a sample of just 10, the actual flights you're gonna get are gonna be jumping around quite a lot. Like you might just by chance get like a bunch of flights that were all super delayed. Or by chance, you might get a bunch of flights that were super early. And so, sample size of 10 isn't that large, and that's why that could happen. Like you just get a few flights that are on one side or the other, and it can just completely mess up your numbers. So that's why we see this move around quite a bit. But if we take a larger sample, so let's say we took a sample of like 100 and then took the median of that, right? Now we get 3.5. That looks a lot closer to 2, but that was just one sample. Maybe I got lucky. So let's try it again. So we can do another sample of 100. 1.5, so it's just below 2. 4.5. 3.0. So notice how every time I'm running this, it's still not perfect, but it's clearly closer than the other one was. Because the other one we got like -2, we got 13.5. It was like really wild, jumping all around. But when we used a larger sample, it looks like when we take the median of that, it's getting a little bit closer. And if we take even larger, let's do like 1,000. So I'm gonna just do this on the other line here. So let's do 1,000. Now we get 3.0. We can run it one more time. 3.0 again. Now we got 2.0. So it looks like this seems to be doing kind of a better job, and it's getting even closer. And so this is all related to law of large numbers, because that empirical distribution is getting like closer and closer to what the population is. And then when we take the median of that empirical distribution, it's going to get closer and closer to the median of the actual population. So we're seeing the same trend here with our statistic that we saw with the entire distribution. And so that's kind of interesting as well. All right, so that's statistics. That's basically how we calculate a statistic. That's how we might use it to estimate a parameter. But again, we talked about how statistics have some randomness, right? We saw that. The statistic is changing basically every single time that we take another sample. And so it's really important to have a sense of how much your statistic is going to vary, to get a sense of how close or how far might you be from the actual value. And so this is where now we talk about the context of a statistic having a probability distribution. So, given that the statistics vary randomly every single time, we take a different random sample, we get a slightly different number, you could say that the statistic itself has a distribution of all the values it could take. So sometimes when we had the sample of 10, we saw one value of the median of 13.5, and another time we saw a value of -2. So the statistic can take on many different values, right? And so the statistic itself actually has a probability distribution too. So it has all different possible values that it could take, and it has probabilities that it could take those values. And what we saw when we increased the sample size to like 1,000, we didn't really get any values that were like 13.5. So the probability of getting 13.5 in a much larger sample seemed to be much less than it was when you had a smaller sample. So that's kind of interesting. And so you can see how there's distribution there that maybe changes. And the basic idea here is the distribution of your statistic is kind of dependent on the sample size you're taking. So like the distribution of the statistic for a sample size of 10 is going to be very different than the distribution of the statistic of sample size 1,000. And so that's an important fact for us to keep in mind as well when we're trying to estimate some parameter. And so ideally, again, what would be nice is if we knew the theoretical distribution of the statistic. So, if someone wanted to estimate the median of all the flights and they only had a sample size of 10, it would be really nice if they would have a sense of what the probability distribution is of the statistic. Like how often is this statistic going to be 13.5 versus -2? It'd be nice to be able to understand that, because then they could report their answer with a little bit more context. Instead of just giving the answer like whatever first number you get, I got 13.5, that's my best guess. Instead of reporting that, it might be nice to be able to say, well, 13.5 is what I got, but actually the distribution of this statistic looks like this, and therefore it could probably be any of these values. And so that just would be a much better answer to the question than just giving one number. But in practice, that's really hard to do. There's like so many different possible values your statistic could take, and typically you're just going to get to see one sample, like we saw. We saw that one sample of 10. And so it's going to be hard to actually be able to do like infinitely many samples of 10 and figure out what all the possible values of the median could be. So in practice, it's hard to do, but one thing that we can do is we could simulate. So if you do have a way to simulate from your random quantity or your population many, many times, then you can actually see at least try to guess what the distribution of the statistic is. And so that would be the empirical distribution of the statistic. And so the idea is the statistics such as the median of 10 flights, that has some actual probability distribution. There are specific values that it can take. There are specific probabilities of it happening. And this is very hard to actually figure out, that entire distribution of all the possible values. So one thing we could do is we could simulate many, many times samples of 10 and take the median. And then that would give us at least some approximation of like what the actual distribution of the statistic looks like. And so this is the empirical distribution of the statistic. And so once again, this would basically be all the observed values of the statistic from like all of our simulations, let's say, and then the proportion of times each value appeared. And so this is a pretty good approximation to the actual probability distribution of that statistic, as long as the number of reputations in the simulation is really large. And so we can see some examples of this right now. So let's try to simulate like several times taking like a sample of size 10. Let's just see like how the median jumps around, because we want to look at the distribution of all the different possible values that actually come up. So let's actually do this. So first, let's create a function to help us do this. And we'll call it sample median, and it's going to have one parameter or one input size, and it's going to return np.median united.sample, and then the size of the sample .column delay. And so the reason I'm making this function is because we're going to do some experiments right now with various different sizes of our sample. For starters, we'll start with just 10, but we're also going to want to do the exact same thing, but with like a larger sample. So it's just nice to make a function for this. So we have this function, and so we can now really easily just do sample median with a sample of size 10. And so we get 9.5. And remember, the actual value is 2.0 in the population. So we did sample size 10. I could run that again. I get 7.5. All right, so now we have our function. That's really helpful. And then what we want to do is we want to do the same thing a bunch of times. So we want to simulate 10 samples and then do that like a bunch of times. And so let's actually do that here. So we'll do sample medians equals make array. So we're going to store these values in an array. And then let's actually do 2000 simulations. We'll do simulations equals 2000. And let's do a for loop that will allow us to simulate this 2000 times. So we can do for I in np.arange, non-simulations. And then what are we going to do in each iteration of this loop? We're going to create a new sample median. And so now we can use our function to do this. And then we're going to append it to sample medians. So we'll say sample medians equals np.append sample medians, comma, new median. And so now if you run this, what this is doing is it's going to, 2000 times, it's going to create a sample of 10, calculate the median, and then add it to the array. And then just do that 2000 times. So now we'll have 2000 medians from 2000 different samples of flights. And then we can visualize this. So we can do table column, sample medians, and then we'll just say size equals 10 to make it really clear. And put in sample medians. So let me put this on a new line so you can see it. And then now we have a table with all of the values, all of the medians in it. We can draw a histogram on the table. I'll just do bins equals 20. So I'm not even going to specify the actual bins. I'll just say make 20 bins. And Python will just make 20 bins for us. And so now we get to look at what this median looks like. And so again, this is the empirical distribution of the sample median for a sample of size 10. So it's really specific to the sample of size 10. That's what's really important. So when you have a sample of size 10, the median of the flight delay is going to tend to look like this. Most of the time, the median will be near 0, but sometimes the median is going to be around 10. Sometimes the median is going to be negative. And we saw that because we saw a median of like 13.5. We saw a median of 9.5. So this kind of makes sense. Like sometimes you're going to see really large medians. But again, the median that we actually want to estimate has a value of 2. We don't know that. Just imagine we don't know that. But this is kind of giving you a sense of what different values might come up with if you did a sample of size 10. And so just to review the code here, we did a for loop because we wanted to do this 2000 times. And in a for loop, you specify an array that you want to iterate over. In this case, the array is 0 to 2000. And for each iteration of the array, what are we going to do? We're going to sample a new median from a sample of size 10, and then append that median to this array that we're going to use to just store all the medians. And so this pattern is something that we're going to use again and again. So append just adds a new value to the end of the array. All right, so now we have that code. And so now someone just asked a question, is this distribution going to look different if you did the same exact thing, but with a sample of 1,000 in each iteration? And so the answer is yes. And so let's actually take a look at that. So I've written some code here, and don't worry too much about this, but it's basically actually just the same code I wrote above, but 3 times. So here what we're going to do is we're going to have 3 arrays now. So we're going to have an array that's going to store the sample medians for samples of size 10, another one that's going to store the medians for samples of size 100, and another that's going to store it for samples of size 1,000. And then 2,000 times, we're going to simulate a new median for each of these scenarios, each of these 3 scenarios. And so that's what we do here. So we have our for loop like before, but now we have 3 sets of code. So the first code is exactly identical to what we just did. So this is saying, create a new sample median from a random sample of size 10, append it to the sample medians 10 array. All right, and then this next set of code is going to do the same thing, but with a size of 100. So now we're going to say, let's take a sample of size 100, calculate its median, append it to the sample medians 100 array. And then lastly, we're going to create a new median from a new sample of size 1,000, calculate its median, and append it to that array. So basically, we're going to come up now with 3 arrays instead of just 1. Each of these is going to have 2,000 medians in it, but the medians are different because your first array has medians that were created using a sample of size 10 each time. And then the next one has medians that were created using a sample of size 100 each time. And then the last one is using 1,000 each time. And so we can run this. It will take some time because it has to go through like 2,000 iterations of this loop. So we'll just let that run. And then what we'll do is once that finishes running, we're going to put all the results into a table. So we're going to just take those 3 arrays and then stick them into a table as 3 columns. So that's what we're doing here. So we're saying table with columns size 10, put the array of all the medians with size 10, and then same thing with 100 and 1,000. So we're going to create that table. And then lastly, we can draw a histogram of all 3 of these and see how the distribution changes as you have a larger sample size in each simulation. So we can run this. And so this is what we see. So this dark blue one in the back, that's the distribution that we basically saw up above. It's going to look very similar to that. It's not the exact same one because it's empirical distribution, but it's very similar. And so this is, the dark blue one is when you have a size of 10. So when you have a size of 10, this is saying that if you take a sample of size 10, most of the time the median is going to be around 0 or like 0.5. Sometimes the median is going to be around 10. Sometimes the median is going to be even as low as -4 or 5. And then if you do a sample of size 100, the median doesn't jump around as much. So that's the gold distribution. So if you do a sample of size 100, now the median is closer to 2. It still sometimes can be as high as maybe like 6 or 7 here. And sometimes it can be as low as 0, but it's probably not going to be as high as 10. So you're probably not going to see a median delay from 100 flights that has 10 minutes as the median. That's not really going to happen. And then if you do a sample of size 1,000, well, okay, then pretty much almost all of your medians are going to be like 2 or 2.5 or 3. So that's essentially what this is saying here. So if you take that median with a much larger sample size, pretty much all the time you're going to be like right on the dot. You're not really going to see any weird medians like 13.5 or 9.5 or anything like that. So this is what that's conveying here. And so important thing to keep in mind here is that this is the distribution of a statistic. So with the law of large numbers, the empirical distribution of your statistic gets closer and closer to the actual value. Whereas the empirical distribution of the data gets closer and closer to the probability distribution of the data. So those are kind of the distinctions there. And so that's why for a statistic, you'll pretty much always see something like this. So as you increase the sample size, the empirical distribution of all the possible values that the statistic can be just gets closer and closer to the actual value. Whereas if we scroll up to what we saw here, right here, in this case, what we saw was the empirical distribution of all of the data in our sample gets closer and closer to the probability distribution of all the data in the population. So again, there's kind of two things here, so I'll repeat that. So in the population, you have all these different values. That's the probability distribution. And then there's this one number, which is the parameter that you're trying to understand. So that's like one true value, the median, for example. So that you have this one true value that you're trying to understand, and then you have like all of this data in the population. And then what we want to do is take a sample out of that. And so the data in our sample, that distribution is going to look more and more like the data in the population as we increase the sample size. Whereas the statistic that we calculate from the data, that also is going to have its own distribution, but that distribution gets closer and closer to the one true value, because in the population, there's just one true value. There's no distribution of the parameter. There's just one value. So that's why that should go to like basically just one thing. And so that's what we saw there. All right. So that's statistics. And so that's very useful because, we want to be able to understand things in the real world about a population. And basically the key is if you have a really large sample size, you can be pretty sure that your statistic is going to be a lot closer to the actual parameter you're trying to guess. All right, so now that actually becomes useful in the case of modeling. So when we talk about models, models are essentially just a set of assumptions about the data. And so the models exist in all scientific fields. If you're an economist, you might make models about, how the economy is going to change. If you're a financial analyst, maybe you make models about the stock market. If you're like an epidemiologist, you might make models about the spread of some infectious disease. So, models are prevalent in all of science in many different fields. They tend to involve math, but not always. And specifically in data science, the models that we're going to be talking about involve assumptions specifically about processes that involve randomness. And honestly, like most models are like that anyway, but specifically in data science, we're talking about models that involve randomness. And so that's what we'll call these chance models. I guess, one distinction might be like maybe in biology, you have a model of kind of how the human body works. And so maybe there's less randomness there, like, every human has a heart or whatever it is. So that's maybe like a model, an assumption that you're making about how something should work. In that case, maybe there's less randomness. But in this case, we're talking about specifically things that involve randomness. And so the key question is, does the model fit the data? So, I'm trying to model something about some population, and that involves basically making some assumption about this population. And so does my model about that population actually fit the data that I'm actually observing? So good example of this is, let's say I believe that 5% of UC Berkeley students are independent. That's their political party affiliation. And so if I believe that, I've made a model. That's my model. My model is that 5% of UC Berkeley students are independent. And so then the question is, does my model fit the actual data that we're seeing? And so what's the actual data? Well, first of all, the data could be everybody in UC Berkeley, but I'm probably not going to be able to get that. So what I'm probably going to do is actually sample maybe like 1,000 students or 500 students, and then see what percent of those students are actually independent. And so that's one way I can see whether the data, the actual real world, aligns with my assumption that I've made about this population. And so we're going to do that again and again. So let's actually talk about how do we actually assess it. It's kind of what I said basically, but the idea is if you can simulate data according to assumptions of the model, then you can learn what the model predicts. So if I could, let's say, simulate data of what a sample of size 1,000 should look like, assuming that 5% of people are independent, let's do that first. And then let me compare those simulations to this one sample that I'm actually going to observe when I collect data. Because in the real life, I'm probably only have enough budget to like do one sample of size 1,000, and I've exhausted my budget. I can't spend any more money like sampling people. So let's say I can only do that one time, but I can go over here and I can simulate many, many times what a sample of size 1,000 would look like if exactly 5% of the population was independent. So I could do that. And then I can basically just compare all of my simulations with this one sample that I actually observed and see like, do they actually align, or are they really, really different? If they're really different, then maybe my model isn't actually correct. And so that's the basic idea here. And the one thing to keep in mind here is that someone said, is the model like your hypothesis? Yeah, it's essentially like your hypothesis. And it's a really famous saying that basically all models are wrong. So like any model about the real world is probably wrong to some extent. But the idea is you want to find a model that's like less wrong. That's really the goal. That's kind of the goal in statistics and data science. And so let's see some examples of that. So here's a case that happened in the US, 1965. Actually went to the Supreme Court, I believe. And so there's a black man in Alabama convicted of a crime, and he was convicted. Like he went to trial and he was convicted. Like they said, the jury said, you did the crime, you get the punishment. And so he appealed, and his appeal was that, well, you know, the jury was really biased. It was like mostly white people on the jury. And so some context about how this jury was actually created. So only men 21 years and older were allowed to serve on the jury. So that was like kind of one condition of how this jury was formed. And then 26% of the population in the city is black. So that's another important piece of information. And so the jury panel that convicted him had 100 men, and 8 of them were black. So 8 out of 100 were black. And the population, again, of people in that actual city, 26% were black. So pretty big discrepancy there. And so the Supreme Court ruling basically said that, I mean, it's kind of like a lot of jargon, but basically the key is like overall percentage disparity has been small and reflects no studied attempt for like discrimination essentially. So in English, what this is basically saying is that, or maybe not English, maybe in math, what this is saying is that the percent of people on the jury, that 8%, there is a disparity between the 8% and the 26% of people that are actually black in the city, but it's not so different in terms of chance. Like you could have just randomly picked 100 people and then like 8 of them happen to be black. So like that's just chance. That's basically what the Supreme Court ruled, and they said, you know, it's just chance. 8% is a lot lower than 26. We admit that, but it was just chance. It's just tough luck. And so there's no actual like discrimination that happened when we were selecting this jury. So that was the argument there. And so, again, I'm just going to paraphrase that here. And so what our question as data scientists is, you know, you're saying that A is less than 26, but it's not really that different. Well, let's actually try to put that, you know, to the test. Like, is 8 out of 100 really a realistic outcome if the jury panel was truly unbiased? So would you really see a number like 8 out of 100 if you just sampled 100 people randomly from a population that's 26% black? So let's actually see if that's possible. So we can do this using simulation. And so what we're going to do is we're going to sample at random from a categorical distribution. And so how do we actually do this? We're going to use a new function called sample proportions. And so the way it works is you just call sample proportions, you specify the sample size that you want to sample. In this case, we're going to do 100. And then the population distribution, which is what's the distribution of the categories in the population. So in this case, we're just going to talk about white and black. And so the population distribution is going to be 26% black. And then what this function does is that it returns an array that contains the distribution of the categories in the sample that we took from the population. So, you know, there's 26% black in the population, and this thing is going to return some number that we actually get in the sample. Maybe the sample ends up being 8%, like the actual jury, maybe ends up being 50%. And so let's actually put this to the test. So the first thing we're going to do is we're going to create an array that contains the actual population proportions. So we'll do population proportions equals make array 26, 74. And so let's take a look at what this actually has. And so here we have 26% black, 74% white. So we've created an array that just contains kind of the actual proportion in the population. And if we want to sample from it, we can simulate basically creating another jury. We call sample proportions. We pass in how many we want, which is 100. And then we pass in the actual true population proportion. And so now we just ran it. In this case, we got 25% black. So by chance, we sampled 100 people, 25% happens to be black. And then we can run it again. Now we got 23% black. Run it again. Now we got 33% black. And so on. So I can run this a bunch of times. And as you see how these numbers are changing around, you can probably guess what's happening here. But basically, you know, it's jumping around quite a bit, but we're not really seeing it come down to 8%. But maybe that's just chance. Like I just only did it like 10 times. So we should really try to simulate this like 1,000 times and see how often, you know, something as crazy as an 8% comes up. So let's actually do that. That's a scientific way of doing it. So let's actually create a function that will allow us to do this really easily. So we're just going to call this panel proportion, and all it's going to do is just return the code that we wrote above. So we're just going to do this, and then that's our function now. So we can call this panel proportion. Oh, sorry. And actually, the main number we care about actually is just that first number. We just care about the 0.31, because when we know 0.31, we know the other number. But really, we're just trying to compare this first number, proportion that's black, to the 8%. That's like what we really care about. So let's actually update this function to not only call sample proportions, but actually just return that first number. So we'll call .item0. So we'll do this. And now when you run the function, it just returns 0.35. And then we could run it again, you get 0.3. So this is basically the main number we care about. So I'm just going to have it return that. All right. And then the last step is, now that we know how to simulate a random jury panel and then figure out what percent of that is black, now let's just do that several times. So let's do it 1,000 times. So we'll do num simulations equals 1,000. And then we'll create an array that's going to store our results from the simulation. And then we'll actually run our simulation. So for I and np.arange, num simulations. What are we going to do in each iteration of the simulation? We're going to create a new jury panel randomly, panel proportion. And then let's just multiply it by 100 because we want to know the actual number of people that were black. And then we can say panels equals np.append panels. And what are we appending to the end of this array? It's just the new panel that we just created. So I just ran that, runs pretty quickly. And then lastly, we can actually visualize a histogram of all the possible number of black people in the jury that actually came up. So we can do table with column, do number of black men on panel of 100. So that's going to be the name of our column in the table. And then what are the values going to be? It's just going to be panels. And then we'll draw a histogram. And then I'm just going to put some bins here. np.arange 5.5 to 40. Okay. So let me just make sure I get this right. Yeah. So this is plotting the results of our simulation. So basically what did we do? 2,000 times, we randomly picked 100 people from the population and then calculated what percent of those 100 people were black and then reported that number. So this is kind of what it looks like. And so let me maybe split this to another line so you can kind of see it. So, you know, first create a table with the column of stuff that we want and then draw a histogram. That's the other line. And so we can see here is, you know, we do this 1,000 times. 1,000 times we just randomly picked 100 people from this population, and then we just saw what percent of people in the jury, in our simulated jury, was actually black. And so we can see here that the lowest number we got was like maybe, I don't know, I think that's like 13. And then the highest number we got was 38. So that's kind of what we're seeing here. And recall in the actual jury panel, there were only 8 black people. So definitely seems like the actual data is not consistent with the model that was claimed. So the Supreme Court was claiming that, oh, it's just random. We randomly picked, the city clearly randomly just picked people into the jury. But this is really strong evidence that that was not the case. And so this is an example of the data not agreeing with the model. And so in this case, the model probably isn't correct. So that's your first example of actual data science. So that's pretty cool. So we're a little bit over time, but I do want to show you guys this example because I think it's important. So we have a genetic model as well. And so this is Gregor Mendel. So he's done a lot of work in like just genetics and alleles and Punnett squares and all that good stuff. So you've taken biology, you're pretty familiar with him. And so in this setup, we're going to say that there's pea plants of some particular kind. And so he's studying like some particular kind of pea plants. And then the plant either has purple flowers or white flowers. And so his model is that each plant of this kind has purple flowers with chance 75%. So that's his model. That's his assumption about how this population works, this population of plants, or this species of plants. And this is like regardless of the colors of the other plants. So just kind of independently, each plant has a 75% chance of being purple. That's it. And so the question is the model good or not? And so let's actually try to assess that using simulation. And so in this case, what we need to do is we need to choose a statistic. That's kind of the first step. So in the last example, the statistic that we chose was just the proportion of people in the jury that are Black. That was like the statistic that we plotted in that histogram. So we simulated a jury panel, calculated what proportion is Black, and then made a histogram of that. So in this case, we're going to want to also calculate a statistic. But in this case, we'll try to do a slightly different statistic, because what we want to see is you want to choose your statistic such that like extreme values of it are more evidence against the model. That's just typically like a more intuitive way to show evidence for or against the model. And so this case, what we're going to say is if the percent is much larger than 75 or much lower than 75, that's evidence against the model. And this is the really important distinction, because in the other case, the claim was that, the 8% that was just by chance, and the man who was appealing the decision was saying 8% is too low, like that's just way too low, that wouldn't happen. So in his case, any evidence that showed that the actual proportions were like much larger than that would be evidence against the model. In this case, we want kind of, it's almost like both sides. Like if we see a percentage of purple plants that are more than 75 or like way less than 75, like both of those would be evidence against the model. And so because of that, in this case, we actually care about distance from 75. So the statistic we're going to choose here is actually like slightly different. And so because we care about the distance from 75, in this case, we're going to make our statistic the percentage of plants that are actually purple in our sample and then subtract 25, but take the absolute value. The reason we do this is because if you have a really large percentage, the absolute difference is going to be really large. And if you have a really small percentage, the absolute difference from 75 is also going to be really large. Like if you have like 25, the value of the statistic would be 25 minus 75, and then absolute value is 50. And so that's why we do that. And so in general, you want to do things such that if the value of the statistic is large, that's evidence against the model. And so in the last example, we saw that our statistic was just kind of the proportion of people in our simulated jury that are Black. And so in that case, we saw that almost all of them, actually pretty much all of them, were larger than what was actually observed. And so that was an example. So let's actually do that now with the actual pea plants as well. So firstly, it might be helpful to see that he actually observed 709 purple flowers out of 929. So that was like his actual value that he observed. So let's take a look at what that percentage is. So 76% of flowers he observed were actually purple. So that seems pretty close to the 75. So that's fairly reasonable, but we want to obviously do a simulation to see like, maybe that was just by chance, maybe he got lucky. And so for our simulation, what we're going to do is we're going to say, okay, so Mendel looked at 929 plants. He got 709 that were purple. Let's simulate 929 plants 1,000 times. Under his assumption, that 75% tend to be purple. So we can do this using sample proportions again. So let's call this predicted proportions. And let's do make array 75, 25. And I'll try not to take more than like 5 more minutes on this, but I do want to just show you the results here. So sample proportions 929, and then we'll do predicted proportions. So this is pretty similar to what we did last time in the other example, but basically here we're making an array of 75% purple, 25%, I think it's white, that's the other color. And then we're going to do a random sample of 929 plants, assuming that this is the actual proportion of each individual plant being purple. And so we can run this. And so in one particular instance, we get 73.5%. Can run it again. In this instance, we got 78% of the plants were purple. So you get the idea. So this is kind of similar to what we did last time. And then so let's create a similar function. We're going to call it purple flowers. And then it's going to return the sample proportion. So I'm just going to copy that, paste it here. We're going to take the first item again, so item 0, because we just care about this number here. And then we'll multiply that by 900, or sorry, by 100. So let me split it over 2 lines. So sample proportions, so basically sample 929 flowers, take the first item, which is the proportion that's purple, multiply by 100. That gives you the number, or the proportion of people that are purple, like instead of 7.78, we'll see 78. So it just like moves it up. And we take item 0 because we just care about the first category, which is purple. So now we have our function, and then now we can actually run our simulation. So we'll make an array, and I'm actually just going to copy the code here from up here because it's pretty much the same. So I'm going to take it, put it down here. We're going to do 1,000 simulations again. We're going to call these purples because we're talking about purple flowers here. And then we're going to say, let's call this like new purple. So that's going to be the new proportion of people, or new proportion of plants that are purple. And then this is going to be purple flowers. So each iteration of the simulation, we simulate 929 plants, count the proportion that are purple, and then just store that in the array, add it to the end of the array. So we run this 1,000 times, and then finally we visualize with a histogram. So we're going to have a column, let's call it % of purple flowers in sample of 929. And then the values are going to be purples. And we'll do .hist. Actually, let's just do hist without specifying anything for the sake of time. And so here's what the distribution of the simulated flowers looks like. So if you take a sample of 929 flowers, assuming that each flower has a 75% chance of being purple, this is the typical proportion of purple flowers you're going to see. And so we do this 1,000 times. And so sometimes we got a sample of flowers where like almost 79% were purple. And then sometimes we got flowers where like 72% were purple. So you can see the variability here when we simulate from Mendel's assumption. And so that was his assumption. His assumption was 75%, right? And so this is what the flowers should look like under his assumption. And then we just need to compare this to the actual value that we got. And remember, we wanted to actually make our statistic not just the value that you got here, but we wanted a discrepancy. We wanted to take this and subtract 75 from it and then take the absolute value. So that's in the slides. And so let's actually do that here. So let's actually visualize that instead. So instead of visualizing the % of purple flowers, let's visualize the discrepancy. So discrepancy in sample of 929. If the model is true. And then what are we going to put inside this table? Instead of just the % that's purple, we're going to do the absolute value of purples minus 75. Because that's what we said we wanted our statistic to be. Because we wanted high values and low values to be evidence against the model. So let's do that. And then visualize a histogram of that. And so now this looks like this. And so basically, the more values that we have like away from 0, the more evidence we have against the model. And so someone asked a question earlier, what is large? Like, what's a large discrepancy? How do we know? Like, sometimes under the model, you're going to get a discrepancy of 3, which means that you're like 3 percentage points away from 75. So is that large? Is that small? Like, what is the context of that? That's a really good question. So the context is that this needs to be relative to what we actually observed. So let's take a look at what we actually observed. So what we observed in that one example, an actual example of purple flowers was stored in observed purples. So let's multiply that by 100, subtract 75, and then take the absolute value. And so just to remind you guys, observed purples, I think, was like 76%. Yeah, so that was what was actually observed in his actual sample. And so if you take the absolute value observed minus 75, you get 1.31. And so basically, if you look at where 1.31 is on this histogram, it's like somewhere around here-ish. And so it looks like, you know, it's far from zero, but actually not that far from zero. If you look at, you know, there's so many other values here that are even farther away from zero. So basically, the one that he observed is not that crazy when you consider like these are all the possible ways that you could actually get purple flowers in a sample of size 929 under his model. And so basically, in this case, what we say is that you know, the evidence is more consistent potentially with the model rather than not being consistent with it. And so that's the outcome there. So basically, there's kind of two scenarios in all this hypothesis testing. So you're always going to have like a model and then this alternative viewpoint. So in the jury selection case, the model was that the people in the jury panel were selected at random from that population that was 26% black. The alternative viewpoint is no, they aren't. And then in the genetics example, the model is each plant has a 75% chance of being purple. Alternative is no, it doesn't. So these are the kind of the model and the alternative, and then we create statistics based on those and then try to show whether or not they were correct. So again, just kind of recapping what we did, choose a statistic, and you wanted to measure the discrepancy between the model and the data. So, you know, whether it's just proportion of people that are black, or it's like the difference between the proportion that's purple and 75. Then once you have your statistic that you care about, that you think is going to help you assess whether the model is true, then you simulate that statistic many, many times under the model's assumptions. And then you compare the data that you observe. You typically observe like one sample. So you want to compare that one sample that you observed to all of these models' predictions or simulations. And you know, draw a histogram of the simulated values, compute the observed statistic from your one observed sample. And then if that statistic is really far on the histogram from kind of, you know, the value you care about, then that's evidence against the model. And so that's what we saw here. So in the first example, that 8% was like not even inside, underneath like the histogram of all the possible proportion of black people you could get. Whereas in the genetics example, the distance from 75 from the observed sample was like actually pretty much in the middle of the distribution. And so in that case, like it's not that crazy. It's somewhat consistent with the model. This was the main ways that we do that. So yeah, sorry for going over time. That's basically what I wanted to cover. Next time we'll go over something similar to the genetic model, except you have more than just two categories of like purple and white. You're going to have many categories. And yeah, and I'll stick around for any questions because we did go over a lot. What was the outcome in the flowers example? So in the flowers example, our I guess conclusion was probably that it seems like the data is consistent with the model because the observed statistic is 1.31, and that statistic lies like over here where my cursor is on the histogram. So the observed statistic, the difference between 76% and 75%, that difference is pretty much expected in terms of like all the simulated distances that we got from 75%. So like all the different flowers that we simulated, sometimes we got flowers that are way more than 75% purple or way less than 75% purple. Sometimes we got a set of flowers that were like exactly 75% purple. But basically what you want to see is like how crazy is that actual sample you saw compared to all the simulated ones from your model. And then if you go back to like the jury panel, in this case, the actual thing that we saw, which was 8%, is like not even underneath the histogram. So 8% is like all the way out here. And then all of our simulated jury panels are like way over here. So you can see that the data is not consistent with the model. The model is coming up with very different simulated values compared to what actually happened. In this case, the model is coming up with values that are pretty much in line with what we saw.
Professor Sahai, you might want to stop the recording now.
Oh, yeah.